Okay, yeah, it's really my great honor to get an opportunity to visit Rice University and join this such a nice workshop organized by Qimiao and other people. So just yesterday when I discussed with Qimiao, I found there's some other interest on topological superconductivity here, so I temporarily changed the title, so not talk about anything about Harvard models. So here, what we're trying to understand is when the Cooper pair can carry a non-trivial Berry phase, and what's the possible interesting phenomena, and potentially it could be realized in certain type of doped magnetic biosimilar metals, and we're also open to other material realizations of such exotic topological pairing. So at the beginning, I want to just give a very general picture. So usually we know that the pairing symmetry plays an important role on many topological, on many physical properties. For example, this. I can. Yes. Yeah. Yeah, sorry. So there could be many different interesting phenomena arising from geometric phases. So for example, we will talk about many interesting topological band states. And then the question is, what are the possibilities when we generalize the idea of geometric phase to two particle states and many particle orderings? And then we can also interesting the topological semimetals, and the band topology has been extensively studied by many people in the audience. And then the question here we'll ask is that there are some fundamentally new phases that we can create based on combining these three question marks together. So here I will just mainly describe what's called as the monopole superconductivity as a new member of topological superconductors. And then the idea can be generalized to particle channel to look at the density waves as well as excitons. And then more generally, we're also looking for other further generalizations of this idea to time reversal invariant systems. And then we know that pairing symmetry plays an important role in many physical properties. And every time when there is a new type of pairing order established, it accompanies with a revolutionary idea in many interesting materials and exotic phenomena. So for example, for the superconducting order, that's the focus of this talk. And we know generally as a mean field picture in the weak coupling in the weak coupling regime, and then the pairing Hamiltonian can be described as the coupling of the order parameter superconducting gap function with the pairing creation operators. And then the gap function as the order itself, usually if we have a perfect spherical forming surface, then we know that we can go into different partial wave channels, and the most attractive channel gives rise to the preferred pairing at the mean field level. And in specific materials, there could be correspond to different representations of the point group of the system. And then on the other hand, we also know that geometric phase plays an important role of revolutionizing the quantum materials. So for example, in the familiar case of geometric phase for quantum state, we know that when the system has a time-dependent evolution of the parameter R, and then the quantum state will pick up a non-trivial geometric phase apart from this dynamical phase. And this geometric phase corresponds to the solid angle enclosed by the loop as in the parameter space, and multiplying with the fictitious monopole charge defined in this parameter space. So now what we are doing is basically generalize this one particle geometric phase to the two particle state first. So consider such a Cooper pair state, psi p, which is just direct product of one state at momentum k and another state at momentum minus k. And now if we consider inter-Fermi surface pairing between Fermi surfaces of opposite chain members, and then in this case, the Cooper pair can carry non-trivial barrier phase. For example, here, if you look at the barrier curvature at momentum k, it points upper right towards the upper right direction. And now if you also look at the barrier curvature, look at for state and minus k, you can find that in this scenario, these two barrier curvature actually parallel with each other so that they add up together to contribute to the Cooper pairing state. And then now let's contribute. So basically in the system with inversion symmetry, but broken time reversal symmetry, you could possibly have preferred zero energy, zero center of mass momentum pairing with non-trivial barrier phase for the Cooper pair that can inherit it non-trivially from the band topology, so that we can define the monopole charge for a Cooper pair. And in this case, when we are pairing the state one at chain number 1, the other one from chain number -1 Fermi surfaces, the monopole charge of the Cooper pair just add up together as a double of the monopole charge for the single particle state, leaving as a positive helicity Fermi surface. So now, what's the physical consequences? It turned out that we can define certain gauging invariant circulation field in the momentum space corresponding to describe how the pairing phase winds around in this momentum space. And it turned out that it leads to a topological invariant that corresponds to a total vorticity defined in the momentum space over a single Fermi surface, which is proportional to 2 times the monopole charge of the Cooper pair. Or in the other way, we can say that when Cooper pair have a non-trivial monopole charge, this gap function must be nodal over a single Fermi surface, and it's nodal in a way that's different from all the other unconventional superconductivity where the total vorticity is 0. So it arises naturally by projecting an initially non-singular usual bare scattering interaction, and then after projection onto the helical Fermi surfaces where the superconductivity happening, and then you can see that the monopole charge would push the partial wave channel and give it a non-trivial shift to the unconventional channel. And furthermore, not only that, now this pairing order itself is can no longer be well defined over a single Fermi surface, and it is described by the so-called monopole harmonic function characterized by the monopole charge of this Cooper pair. And it's intrinsically unconventional, well, because you see that the J's partial wave channel must be non-zero when the Cooper pair of monopole charge of the Cooper pair is non-zero. So what's this monopole harmonic function? So let's first take a look at what's the angular, usually spherical harmonic functions are the eigenstates of the angular momentum operator. But in the presence of magnetic monopole, let's say first look at it in the real space. And you will see that firstly, under this radial direction magnetic field, you may imagine system has rotational symmetry. However, because the Lorentz force in this case becomes is not a central force, so that you can imagine the usual angular momentum is no longer conserved. And you can see that the time dependence of the angular momentum actually picks up a non-zero quantity. And however, that non-zero quantity can be reinterpreted as a result from the Poynting vector that contributes to the angular momentum from the EM field from the real space. And then now combining these two terms together, we can define this new angular momentum operator, which is physically conserved when we consider the scattering problem in the presence of a magnetic monopole in real space. So that's even classically. And then in quantum mechanics, we know that such additional contribution is actually quantized due to Dirac quantization. and that corresponds to the monopole charge of the system. So now we can do the same thing in momentum space and study the eigenfunctions of such a modified angular momentum operator. Well, now you see that not only you have the minimal coupling to the Berry gauge potential, but also you have additional term along the radial direction in momentum space proportional to the monopole charge seen by this pair. So, such angular momentum eigenstates is described by this so-called monopole harmonic functions, which intrinsically breaks inversion symmetry due to the singularity and the gauge choices. And furthermore, we can take a look at compare such exotic monopole ordering with the conventional, more conventional known as, say, for example, helium-3A pairing, which is also in the p-wave channel with angular L equals 1. And for example, let's look at M equals 1 channel. And then you have P plus IP pairing well defined over the entire Fermi surface. The gap function has two nodes, one north pole, another one at the south pole of the Fermi surface. And around the north pole, if you count the vorticity relative to normal direction of Fermi surface, it is 1. While if you count the vorticity contribution at the south pole of the Fermi surface, it's -1. So adding up together, it's 0. However, if we look at the same momentum space vorticity defined over a single Fermi surface for this monopole pairing, and then locally you can have a description of monopole pairing near the north pole as P plus IP, while around the south pole, to get it well defined, taking another gauge to describe locally, it's actually plays role as the P minus IP. Now at the south pole, the phase winding changes the direction so that the total vorticity over the entire Fermi surface is 2, which is consistent with the previous derivation of the total vorticity based on the monopole charge of this Cooper pair. So this order can also be discussed in density wave channels, and etc. And here we can also choose a particular tight binding model that I didn't, I'm not showing the details, but we can have a scenario that look to study the, so that we can study the surface states in this system. So, so for example, let's take, for example, the x equals 0 surface and look at the energy spectrum of the system and plot it versus the good quantum number ky at a different fixed momentum kz slices. And if we look at the first slice near the north pole of the Fermi surface, as we described locally, the gap function can be described as P plus IP, so that you see a Majorana modes with the upgoing trend with a positive group velocity along the y direction. And then if you look at another kz slice near the south pole of the Fermi surface, because the gap function locally described as the P minus IP, so that you see the curve start to change the sign, to move downwards at the ky equals 0 point. And that gives rise to a Majorana states with a negative group velocity. And then if we take another slice away, slice 3, away from the Fermi surface, then you cannot see much effects from superconductivity. What you see there is just Fermi arc and the BDG counterpart of it. So, so put together, you can see interesting, not only the wild electron and the hole arcs, but also you can see nearby the Fermi surface, the contribution from superconductivity give rise to the Majorana arc connecting the nodes of this monopole superconducting order through the surface projection of the Fermi surface at the surface Bresel. So, so as we go from slice 1 to slice 2, there is an area that you can see a large contribution of density of state at 0 energy. And then this similar situation, if we consider different pairing, but in the same, but from the same band Hamiltonian. And then you can see that, for example, you can change the pairing so that reverse the chirality locally at the North Pole and the South Pole. And then, however, you will see 4 outgoing nodes at around the equator of the Fermi surface. And then in total, there's total vorticity is a topological invariant only determined by the monopole charge of the Cooper pair, which is 2. And then you can see similar scenario as the surface spectrum, where you would expect large zero energy tensile states contribution. And then as a quick summary here, you can see that if we compare this monopole pairing with other known pairing before, for example, helium-3A type pairing, where time-reversal symmetry is broken and there's non-trivial phase winding around each gap node, but the total vorticity remains 0. And comparing with helium-3B, which is time-reversal invariant and system characterized by a real d-vector contribution, which is topological invariant based on the punctuation number of this d-vector. And here in this monopole pairing, time-reversal symmetry starts from a magnetic Weil system, and its time-reversal symmetry already broken. And then this pairing is intrinsically nodal, dictated by the Berry phase of the Cooper pair. And then the existence of the node is independent of specific pairing mechanism. And you can see that this pairing is actually a type of non-unitary pairing with complex d vectors. And then as for the material realization, what we are trying to consider is such a system from the Dirac semi-metal system, which can go superconducting. And then in this cadmium-3 arsenide CD3S2 system, it's characterized by the 4-fold rotational symmetry along the z-axis. And in the presence of, say, a Zeeman splitting, Zeeman field along the z direction by Zeeman exchange field. And then the symmetry is reduced to C4V. And then as the early work by David Vanderbilt's group, which shows that each Dirac node can be split into 4 Weil nodes of ±1 and ±2 chiralities. And based on his model, my students and I tried to work on the specific pairing in the system. For example, we can consider different allowed pairing belong to different representations. Here, for example, if we consider this BU representation, and then when this chemical potential is up there, and you would see the at the half of the brain zone along the you will see a C equals 1 electron pocket at the upper part of the brain zone with Kz larger than 0. And if we consider pairing between the C equals 1 and the C equals -1 Fermi surface in this BU representation, and the student look at system and found if we look from the south pole and from the south part and from the north part, you observe non-trivial phase winding of this order parameter nearby the superconducting nodes, and they wind in the same way so that it contributes total vorticity equals 2. He also studied, basically goes through different possible representations allowed by the system symmetry, and you will see rich patterns of the pairing nodes, but this total vorticity remains invariant. And you can also go to more exotic case to look at even monopole charge equals 2 pairing in the system. And then you would see this total vorticity over a Fermi surface surrounding the Fermi surface formed by the electron pocket. And then the total vorticity becomes -4. And so far, besides this nodal feature of this gap function, we're also looking for other phase-sensitive probes that can possibly identify the monopole charge of this Cooper pair. So what we're considering is the following. So we know that the physical angular momentum in this system is, for example, characterized by in this m equals 0 channel. as an example. And then now, if the nodes are aligned along this KZ direction of a Fermi surface, now let's consider a junction of a Josephson junction between such a monople superconductor and the S-wave superconductor, also along the Z direction, so that the rotational symmetry along Z is preserved. And then because both S-wave and this monople superconductor have this Z component angular momentum 0, so that the Josephson coupling as the first order is non-zero as shown as the pronounced feature based on tight binding calculations. And we can also do similar as for example, the corner junction, and which shows the S-wave like feature as shown in this red curves, comparing with, for example, chiral P-wave, Px plus IPY type pairing, where it's decoupled from the S-wave superconductor in the first order Josephson effects, and shows the time reversal symmetry breaking feature at the Fraunhofer pattern in the dashed line. And then, but someone will say, well, this looks just like an S-wave, but it's not S-wave. So for example, if we consider putting two identical monople superconductors aligning shoulder by shoulder along to make sure that, for example, Kz is a good quantum number and build up a junction along the X direction. And then you will see that non-trivial coupling contributed by this pairing angular momentum locally well-defined at the North Pole as well as the South Pole, which give you the same contribution as the planar junctions made by Px plus IPY with Px plus IPY superconductors. So, so combining these two sets of experiments, we can identify the shift in angular momentum from the local description to the physical, to the global angular momentum in the system. So in this co-pairing system. So at the end, let me thank all my collaborators, and will Junyi Jiang, who is a postdoc fellow at Johns Hopkins, and actually he's in the audience. And then, yeah, if any questions, please feel to ask him. And there are also lots of contributions from students and previous students in my group, and also Professor David Haldane for the early stage collaborations of this work, as well as David Vanderbilt and Nitin Samas for further push towards the materials. Yeah, let me thank everyone.
Thank you for the excellent talk.
Thank you very much. Thank you very much. I have a simple question. One is about when you told us about different slides as part of that. When I think of the interface, the people with zebra case not doing well. So we don't really know about that. What would that be by? What would the prediction be?
You mean the surface states, or okay? Let me see.
When you show surface states, I think it's slides. What would it be like?
Yeah. Oh, let me see if I have a better. So yeah, so if you look at the zero energy locus, that's located at the lower right corner, so the sketch of zero energy locus in the momentum in the surface burn zone. Sorry, let me see if I can use. Yeah. So so here are the locations of the previous Weyl nodes in the surface projection, and then you have Fermi surfaces to the projection of Fermi surfaces to the surface burn zone, as shown in this little dashed circle. Sorry, not very visible here, and then these two dots here correspond to the location of gap nodes, right? So away from the Fermi surfaces, what you see is just a Weyl Fermi arcs. And there's a particle version and a whole version if you do BDG. While here you will see nearby the Fermi surface projection to the surface burn zone, you will see the Majorana arc connecting the projections of gap nodes here.
Can you say a little bit more about the connection to the experimental candidate? So was that for just other magnetic field or magnetic doping plus field?
Yeah, I would say magnetic doping would work because otherwise the Zeeman we need a Zeeman exchange to really push.
If you don't have the magnetic doping, it's like that magnetic field mostly does all the time.
Yeah, or if you know some magnetic vial semi-metal system can go superconducting, that will also work. Yeah, or other potential materials we know already superconducting and with magnetism around and with potential topological physics around. This is a good question. Yeah, so the question was if it's possible that this node could be kept by CDW order. I think, PDW order. I don't. Yeah, I don't think so. I don't think so. But if you, well, because here we constrained our discussion to the interferometer surface pairing. And if you are considering, say, competition with other types of pairings, that could be gapped out.